All right, so in this third section of the video series on Broyden's method, we're going to be applying Broyden's method to optimize a certain function subject to a certain constraint function. And to do this, we need to introduce the idea of a Langrange multiplier. So we'll define f as the function that we're going to optimize or minimize in this case. And that's going to be a function of x and y, and we're going to be minimizing that subject to a constraint g, which is another function of x and y. Now, a Langrange multiplier is a multiplier that allows us to be clever in how we perform this optimization and ultimately apply Broyden's method. And the Langrange multiplier is used like this. We have the gradient of our function f is equal to some multiplier, which is the Langrange multiplier of our function g. Some multiplier of the gradient of our function g, that is. Now, ultimately, the way that this plays out, instead of applying Broyden's method directly to f, we instead define a new function, which is L, of now three variables, x, y, and lambda, which is our Langrange multiplier, where this is f of x and y plus our multiplier, lambda, times g of x and y. Now, once this is set up, we're going to look at our gradient of L, so our partial derivatives of L with respect to x, y, and then our Langrange multiplier lambda. So it's going to be partial of L with respect to x, partial of L, partial y, partial L, partial lambda. All of these are going to be equal to 0. So the overall, facing the wrong way, the overall gradient of L is going to equal 0. And what that tells us, or allows us to determine, is that this Langrange multiplier is going to be negative, actually, which will make a little bit more sense once we look at the graphical representation of this, which we'll look at in just a moment in the next portion of this video. All right, so now to actually code this out, like I mentioned on the whiteboard just a minute ago, using our Langrange multiplier, we have that the gradient of our constraint function g is a multiple of the gradient of our minimization or our target function that we're looking to optimize, our function f. And these are both functions of x and y. And when we set the gradients all to 0, we see that the Langrange multiplier is actually negative, and that indicates it's a little bit easier to visualize if we go to the Wikipedia page for the Langrange multiplier. It's a little bit easier to visualize here when we're looking at a function in 3 dimensions, or I guess 2 dimensions here. We see that the minimum of, or in this case, the maximum of our objective function f with the constraint g of x and y, the maximum that we get is when the gradient of our constraint function g and the gradient of our objective function f are collinear. So those are collinear, they're moving in opposite directions, which is why we see that negative sign. So when we actually go to code this out, we'll see that our Langrange multiplier ends up being a negative number to indicate that those gradients are in opposite directions. And this is where our optimum result for our function f, the optimum position to maximize that subject to the constraint, is located on this graph here. Now, for our purposes in this video, we're going to be looking at the Rosenbrock function in 2 dimensions. More commonly, it's used in 3 dimensions, but it works for 2 dimensions as well. And the Rosenbrock function is a function that's used to test optimization algorithms like the one that we're going to be looking at today. So we see that our 2-dimensional field here, we've got this gradient over here on the right of color, where the lowest values are this like darker blue. So we see that those minimum values lie kind of on a parabola here. And it actually says here that the actual minimum, the true global minimum of this is at 1, 1. So that puts us like right about here, right inside of that V-shaped valley where those negatives are low, or where those function values are lowest. Now, the constraint that we're going to be imposing on this Rosenbrock function is that our result needs to lie on a circle centered at this point with a radius of 0.5. So that puts us in a circle that surrounds that point. So we're not going to be at that point. We're going to be at a point on that circle which is likely going to put us somewhere in this region because we see that those low values are in that V-shaped parabola here. So the x will be between 0.5 and 1, and then so will the y value. Those will both be between 0.5 and 1 because we're kind of in this region here surrounding that true global minimum. So now let's go to code that out. We'll start by importing our necessary libraries that we're going to use. So we're going to use NumPy, we're going to use JAX, and we'll set JAX to 64-bit. Just to get the resolution that we're looking for. And then alrighty. Oops. Oh, I think we got that in the wrong order. x64 enable. There we go. Oh, geez. Okay. Total autopilot. All right. x64. There we go. Excellent. Very good. So now we will define our Rosenbrock function. So that will pull in an array of two values. We'll unpack that as x and y. Then we will return. Let's go back and look at this real quick. So we've got, so a is 1, b is 100. Okay, so that's 1 minus x squared plus 100 times y minus x squared squared. Okay, so y minus x squared and x squared on the outside. Great. All right, now we will define our circle constraint as well. It's going to look pretty similar. We'll unpack that vector coming in, that array coming in. This is going to be a circle centered at 1, 1 with a radius of 0.5. So we'll do 1 minus x squared plus 1 minus y squared minus 0.5 squared. Alrighty, so once we've got our Rosenbrock functions, our objective function that we're looking to minimize, and then also our constraint function, which is the circle here, the first thing we're going to do is use the SciPy optimization, the SciPy minimization formula, or like built-in algorithm with Python here in the SciPy library, and see what that result is, and then we'll write our own algorithm using the Broyden's method and compare the results of those two methods. So we will say that x guess, our initial guess, we will say that this is the origin, so we'll say that that's 0, 0. So we can say the result that we're looking for is minimize, and then we'll call a Rosen function. We'll say that our initial guess is x guess, which we defined just up above. Constraints equals type equals equation, and then we have to input our circle constraint function, circle constraint. All right, and then we'll look at what that result is, see what that gives us. All right, so we're looking at, these are the results that it found. So we've got 0.7528 and then 0.564. Now let's go back to our Rosenbrock function and see, we'll zoom in a little bit, see if that makes sense. So that's going to put us, let's see, 7 right about here. And then we'll look past 0.5. So it's looking like it's going to put us like right about here, which I think is a good estimate. Or not a good estimate, it's actually calculating that. That's a good result. That matches what our intuition would tell us where that minimum would be along this this parabolic curve here. So that makes sense. So we'll look for that same result with our Broyden's method that we're going to code out manually. So next we're going to set up that Lagrange function. Like I mentioned in the previous part of this video, we've got a Lagrange multiplier here, and then instead of minimizing just f, we're going to actually be minimizing L, which is a new function that we define as a addition of our objective function and then our constraint function multiplied by the Lagrangian multiplier here, which we symbolize with lambda. And instead of lambda in this, we'll use L, just so we don't get confused with our symbols and have to type too much, like if we were using a lambda function, for example. So Lagrange, this is going to pull in an array as well. We'll unpack this a little bit differently. So L is going to equal the last digit in that array, and then we're going to return Rosen times plus L times circle constraint. All right, cool. And then this is going to be the first two values coming in. There we go. This is also going to be b colon 2. So this array coming in is going to have 3 elements to it. The first 2 are going to be those x and y coordinates. And then the last one is going to be the Lagrangian multiplier here. So that's what this is returning. And then just to plug into our Broyden's method here in just a moment, you'll need to define our Lagrange Jacobian is equal to Jacobian of Lagrange. Oops. Oh, equals something there. Excellent. All right, so now we will define our Broyden's method. So we'll step through this this algorithm here. So we'll take in a function, and then we'll take in an initial guess, x1, and then we will take in our, we'll also define maximum iterations is going to be 100, and then our tolerance for our final function value is going to be, let's say 1e to the negative 10. All right, so the first step is going to be initializing some of our values. So we will initialize our first function value, so fl1 is equal to f of x1, and then we'll initialize the norm of our function value as well. Oops. And then lastly, we will initialize, we will initialize our Jacobian here as our identity matrix. So I, x1 dot size. Great. So we'll have 2 nested loops. The first one is the outer one is going to be the loop that actually steps through our Broyden's method, as we talked about before, in the style of the Newton's method. But there will be a smaller loop inside that is going to be a line selection that's just going to look at picking a step size that will reduce the norm of our function value. So that gives us the step size to proceed within the Broyden's method. So we will do for I in range max enter. The thing we're going to do here is define our dx is j end fl1. We'll have our next our next loop. We'll do this 10 times. We probably shouldn't need to do that anymore. So we'll update to x2, and then we will proceed similarly up here. fl2 is equal to f at x2, and then fl2 norm is going to be just the same thing. At this point, we're going to check and see if the norm of function value 2 is less than the function value of 1, because that's what we're looking at to indicate that we're looking at the right step size. And if that's the case, we'll break out of this loop back into the outer loop. So if fl2 norm less than fl1 norm, break. And if not, we will take our step size and then, yep, plus equal, divide equal 2. Alright, now outside of this loop, we're going to print I, so the iteration that we're looking at, x2 and fl2, so norm. And then the next up here is going to be reshaping some of our values here for the next iteration. So dx equals dx dot reshape, -1.1. And we'll define and reshape df here as fl2 minus fl1 dot reshape -1.1. And here's where we will update our Jacobian using Broyden's method. All right. Lots of matrix multiplication in here. So we'll do dx dot t, jn divided by 3 terms. So we've got dx transpose at jn at df. All right, so that should be Broyden's method for the Jacobian update that we derived in the previous videos in this series. So now we will update some of our values. So x1 is equal to x2, and then fl1 is equal to fl2. I think I missed a break here. Yep. Well, let's do this before I forget. So now we're going to return x2. So here, we actually want to have another break. So if jnp dot Langrange dot norm of fl2 is less than the tolerance, then we want to break out as well. Otherwise, we'll go through all of those maximum iterations, which would be 100. All right, so let's see what we're looking at. All right, so that worked. Let's see if it actually works if we run it. So now we'll do Broyden's method. Now the incoming function is going to be the Lagrange Jacobian that we defined up here. Lagrange Jacobian. And then our incoming array is going to be a row concatenation of our x guess, which is just going to be 0, 0, because we already defined that up above. So where do we define that? Yep, there we go. And then we also need to supply a guess for our, for our Lagrange multiplier. And we'll just say that that guess is going to be 1. All right, let's see what we're looking at. All right, looks like it's going through, it's going through, it's going through. All right, something's getting goofy for sure. Oh, maybe not, maybe not. Yep, looks like that actually worked. All right, so let's now compare and see if we're getting the same numbers as above. So looks like here we're getting 7528, and then here we're getting 7527 and change. And then here we are going to get 5654. We get 5654. Alrighty, so the result from our Jacobian method algorithm is that we get the same optimum solution. So that again is the minimum value in our Rosenbrock function in 2 dimensions, subject to the constraint of the circle. All right, and just one small adjustment to what we were looking at earlier. It looked like these indices here got all messed up, and that's just because I used the same index for both loops. So if we go and change this to j, we should be good. So let's run that again and see if those indexes on the left, as we're running down, look better. The values were correct. There we go. Okay, yeah, so the values that we resulted in were correct. Again, it matches our minimization here that we were doing with the minimize function in SciPy, the SciPy library, but those indexes over here on the right for our iterations were looking a little goofy. But again, same results and they match perfectly. So again, this has been Broyden's method, using Broyden's method to minimize the Rosenbrock function given the constraint of a circle centered at 1, 1 with a radius of 0.5. Thanks.